Welcome back to ECE 320A. We are now in our last lecture of material. The next time we meet, which is next Tuesday, it will be a review. Not sure what all that will encompass, but we'll try to have a review on Tuesday. And the homework assignment, somebody was asking about figure 15.1 in that homework. That's actually in yesterday or Tuesday's lecture notes. One of the first figures that was displayed was figure 15.1. So if you don't have access to that figure, you do now. If you just look at the first page or bottom of the first page, top of the second page, hopefully you can cut and paste that to figure out what figure 15.1 looks like if I don't get that uploaded separately into D2L. Our final exam will occur on a Wednesday. What's today? Thursday? Yeah, I'm so mixed up. So this is less than 2 weeks from today is the final exam, and it will occur from 1 p.m. to 3 p.m. in this room. So make sure that is on your schedule. Today what we want to do is summarize, refresh our knowledge of three-phase power. And here is sort of an outline. I'll just give you a diagram just so we are oriented where we know we're at. We'll talk or just remind ourselves of the different phase sequences, ABC and ACB, or positive and negative. We have the two different kinds of interconnections at both the source and the load, and so you can mix and match those, but we have delta interconnections and Y interconnections, and those actually lead to you having to make sure that you are aware or clear on the difference or the distinction between phase variables and line variables. And we'll try to talk our way through that for different interconnection structures. Complex power, you can write that many different ways. And here are some ways that you might see it written. And hopefully I have maintained an overbar on the quantities that are actually phasors. S, complex power, is a complex number. Maybe it's not so much a phasor, but I just have indicated it's a complex variable by that overbar. That's VI star in general, voltage across an element or elements and the current through those elements. Or it's P plus JQ, or in terms of magnitudes, it's VI. Those are two just magnitudes, cosine of the difference between the voltage phasor and the current phasor. Then you have the reactive piece, which is the same magnitude-wise. You just are now looking at the sine of that angle. That's the Q. I find it helpful to just sketch the complex power triangle. When I'm thinking about these, I just draw a triangle. The hypotenuse or Pythagorean just makes me feel warm and fuzzy, so I just draw that triangle, and then I'm more comfortable talking about P's and Q's and which direction I'm headed in terms of Q. Is it a lagging or is it a leading relationship on my voltage and current? And then we'll work through some problems. That's the idea, so that we can become a little bit more, and I guess the step between working problems and complex power is we can up it by a factor of 3 by going to three-phase. In the three-phase environment, if we're balanced, then if we know the complex power in one of the phases, we can just triple that, and that's the complex power total, which is my S sub T. The confusing part maybe for as we're starting to learn that is you can also write that as the square root of 3. times VI, but now these V's and I's are magnitudes, and they are line variables, whereas the variables inside S sub phi are the phase variables, the phase voltage and the phase current of a particular element or subsystem. We'll try to make that clear as we're going through the notation or the terminology, and also during the solution to these worked problems. Here's the picture that you can maybe keep in mind. We have generation and then we have consumption. And in between that is sort of where we deal with. We may not worry so much about the transformer stepping up the voltage and the transformer stepping down the voltage, but we are interested in what are we generating power-wise, complex power, and what are we receiving. As a primary customer, I know we don't like to be referred to as secondary, but we are secondary customers generally, unless we're at a larger manufacturing facility or another industrial plant. Then you might be a primary customer, and your voltage levels coming in are much higher at that location than they are if you are a secondary customer. Just sort of a way to think about this concept of three-phase power. And don't get too hung up on the voltage levels. On an exam, who knows what the voltage levels will be, but in practice they could be 765,000 volts for a high transmission line, and coming into your house it's going to be the 120 split different ways so that you could actually get 240 if you want. But then if you're a higher customer than secondary, you might have a higher voltage that you're dealing with initially at your gate or wherever you are allowing the power to come into. Here is my attempt at reminding myself about these phase sequences. The blue is supposed to be an I. So you're watching these three phasers spinning. They're spinning counterclockwise. That's what the red arrow is supposed to be indicating. But that now says, oh, these are spinning at omega. But the A phase, the B phase, and the C phase, if you just took a snapshot, they are related by this relationship. And here I've actually drawn them for a balanced phase sequence where they're now 120 degrees apart. They split or divide this 360 degrees evenly among them. But the reason I've drawn that I is if these phasers are now spinning and you're standing here watching, if it's a positive phase sequence, you see the A phase, then you see the B phase, then you see the C phase pass by you as it's spinning in a counterclockwise direction. The negative phase sequence, the ACB, you see the C phase after the A phase. And that may or may not be necessary to know depending on the problem that you were asked. But typically, you will be dealing with balanced three-phase systems, and you'll have to then say, oh, let me just assume a reference. Maybe that's the voltage at maybe the terminals of the load, or maybe it's the A phase at the load. You just say, there's my reference, and you call that 0. And then everything is relative to that. And as I had indicated earlier, we have the two different ways that we are interconnecting sources and loads, either in a Y or in a delta, and that influences which quantities are considered line voltages versus phase voltages, line currents versus phase currents, etc. Let's look, see if I have the right sequence. Here's a YY three-phase interconnected diagram. And here below is the C phase. I'm going to focus on the A phase so that we can make sure that we're clear on the terminology. In this YY configuration, the line current is the same as the phase current. The reason that is the case is because that current, I sub AA, does go directly through the load, Z sub AN, and it also goes directly through the generator. So now your line current in this YY configuration is the same thing as your phase current. If I say, oh, what's the current in the A phase? You know that it's now the same as the line current in the A phase. Contrast that with the voltages at, let's say, the load side. The voltage across the A phase impedance is what I'm labeling V sub capital A capital N. It's the voltage from terminal capital A to terminal capital N. That's not the same as the voltage across terminal A and terminal B. Terminal A to terminal B, that's our line voltage, transmission line. We just throw the transmission out, but keep it in your thinking. When we say line voltage, it's really transmission line to transmission line that we are measuring. And if you just have your load buried inside terminals, you may not be able to access capital N. So you may only be able to measure those terminal voltages or your line voltage. But here in the Y configuration, your line current and your phase current are the same. Your phase voltage and your line voltage are different. Have you gone through that? You know that, or you've seen that? And now, let's say we had a Y delta. Now things just flip in terms of they change. Now the A phase load voltage, which is V sub capital A capital B, that's the same as your line voltage at the load, because it's the voltage across that A phase impedance. Contrast that now with the current. Our line current, which is still I sub A little a capital A, now it gets divided differently at the load, so that our A phase load current, which is the current going through our A phase of the load, that's capital I sub capital A sub capital B, is not the same as I sub lower a capital A. And now I hope you can appreciate the fact that depending on the interconnection, whether you have a Y or whether you have a delta, you have to know if somebody says, well, what's your phase voltage or what's your phase current? You have to know, well, what's the interconnection structure? So here is the emphasis. The A phase line current, now I'm saying phase in two different ways, or using it in both cases, that's not the same as the A phase load current. The A phase load current is I sub AB. This is for the delta connected load. That's not the same as I sub A, little a, capital A. Whereas in the Y interconnection, they were the same. Let's not go through all of those. So now let's look at complex power. Complex power, and for now, let's just focus on the single phase. Now if we have, let's say, Z sub phi, our impedance, then what we're interested in is now this voltage and current. Well, maybe I don't need to subscript that. Voltage and current associated with this load, this impedance. The complex power is now V I star. If you need to find the complex power associated with that impedance, you would then need to know the phasors, both voltage phasor and the current phasor, across and through that particular impedance. That now allows you to rewrite this complex power expression many different ways. Suppose that we now used Ohm's law in general, and we said, let's replace V with Zi. Now what do we have for an expression for the complex power? What's a complex number times its complex conjugate? That's the magnitude squared, isn't it, of that complex number. So here we could say, oh, we have the magnitude of our current squared times Z. Meaning, if somebody gives you the magnitude of a current and you know the impedance, now you can find the complex power without worrying about V and I star. It's just magnitude I squared Z. Or you could now say, well, I don't know the magnitude of the current, I know the magnitude of the voltage. Let's now replace I star with its Ohm's law relationship, or now we have V over Z star, so that in the numerator, again, we have a complex number times its conjugate, or this now says, oh, we have the magnitude of V squared over the complex conjugate of our impedance Z. And once you have this S as a complex quantity, then you could write it in rectangular form. And I don't know what I want to write. Who knows if I'm going to... maybe that's not the best, huh? So let's say this is S, and now this is P plus JQ. In this way, we now could think of this complex power in terms of a triangle. We have the real power, or the average power, that's P. We have the reactive power, Q, which is given units that are distinct from watts. That's the units on power. This is now VARs, volt amperes reactive. And now that allows us to find the hypotenuse, or the apparent power is just the magnitude of that complex power, and the angle is phi, and we can relate that to Q and P. Which, if somebody now said, oh, what's the power factor? That's now the cosine of phi. And do they just give you a number when they provide you with the power factor information? Do you need to know anything else? Cosine of phi is going to kind of get rid of whether that phi was positive or negative. So you have to tell us which direction. Was Q positive or was Q negative? If it was positive, then we have a lagging power factor, or the current is now lagging the voltage. So you have to tell us, is it lagging or leading? Where this would be Q bigger than 0, and this is Q less than 0. I've sketched the power triangle for a lagging or an inductive type load. And I haven't sketched a more capacitive type load. But now that we have complex power, this is for one phase, we could now say, oh, I can use that to determine my total complex power in a three-phase system, especially if it is balanced. So if we now look at the balanced situation, now we have even more ways of expressing the formula for this. The most direct is just to say, oh, if you give me the complex power in one of the phases, and if it's balanced, I know all three phases are giving or yielding the same complex power, I can just triple that and obtain the total complex power of the load and transmission lines, of your generator, etc. And now you could say, oh, I can now express S sub phi. Let me go ahead and just say S sub phi is now the magnitude of my phase voltage, which may or may not be the magnitude of the line voltage, depends on how it's interconnected, times the magnitude of my phase current at an angle of, so now I'm writing this in phasor form, theta sub v minus theta sub I. And a lot of times you might actually see this just saying, oh, that's the impedance of this element or device. The angle of the impedance. That's theta sub v minus theta sub I. Are we comfortable with how to relate magnitudes of phase voltage and line voltage for a Y-connected load? Do you remember the magnitude change and the angle change, if you're relating those? If we now had a three-phase load, suppose now that and I'm assuming it's balanced, so all of these impedances are the same. And at the load side, I think it's this textbook's notation to use capital terminal values, which now if we wanted to know the relationship between this voltage and this voltage, do you remember the expression for that? How are those two phasors related? This is balanced. Did I say that? Maybe not, but I indicated it by the z sub phis. And I'm going to say it's an ABC sequence so that we have a way of assigning phase values for the A phase voltage and the B phase voltage, which is this voltage V sub B in there. across your B phase impedance. We can now find the relationship between those. Stop. By simply doing a KVL there in terms of these variables. We can now say, oh, minus V sub AB plus V sub AN, I ran out of room, minus V sub BN, and then I'm back where I started. We okay with writing KVL in that little loop. Now we've related line voltage, V sub AB, to phase voltages, V sub AN and V sub BN. By assuming I have a ABC sequence, if I now say, well, let me just make this A phase my reference phasor, and I'm just going to say that that's some magnitude of my phase voltage, V sub phi at 0. What is V sub Bn as a phasor? We're balanced. You have two parts of this, and the first part shouldn't count. But it will, probably on the final. You'll have to know that. What is it? If it's balanced, it's exactly what the A phase magnitude was. The only distinction between V sub AN and V sub BN is its angle. And if somebody says, oh, let's just derive this for the positive phase sequence, ABC, you now know the magnitude and what's the angle. Now you have to remember how you were getting hit when you were standing there by those phasors as they were flying around in a counterclockwise direction. It was A, B, C. So B was 120 degrees behind the A phase. We now can say we have that for our angle on V sub Bn. If you now plug those values in from here, we can say, oh, V sub AB is just V sub AN minus V sub Bn. And that now is V sub phi at 0 degrees minus V sub phi at minus 120 degrees. If you just go through the complex algebra, complex meaning complex number-based algebra, you will see, and I'll spare you the details, but you can go home and do this if you haven't done it already. You now find that this is now the square root of 3 at an angle of 30 degrees different from V sub phi. And V sub phi was actually what we had assumed our V sub AN was. If you now want to know how do I get my A phase line voltage from my A phase phase voltage in a Y interconnected load, I just change or alter my phase voltage by a magnitude of the square root of 3. I enlarge it, and I rotate that phasor by 30 degrees. That's the connection between V sub AB, the line voltage, and the phase voltage V sub AN. That being the case, now the reason I was doing that is if I now wanted to rewrite some of these total powers in terms of line voltage and line current magnitudes, maybe I don't want to keep track of phase voltage and line voltage, phase voltage and phase current to determine my total phase. Maybe I want to go out into the field and measure what's the line voltage and what's the transmission line current, and then I'll know maybe the power factor, and I can figure out what my angle is. I can tell you the total complex power. Can we now rewrite this, replace these phase voltages with line voltages, and derive the relationship for total complex power? Here we have now determined the relationship for magnitudes between phase voltage and line voltage for a Y-connected load. We now know that V line magnitude is equal to the square root of 3 V phase. Or if we now want to, if we just keep track of and say this is just a magnitude, we now know the phase voltage magnitude is V line over square root of 3. Now we can say, oh, well, the total complex power is 3 S phi. But that was now 3 times V sub phi, I sub phi, angle of theta sub phi. But now we have a way of, and if we have a Y-connected load, what's the phase current in terms of the line current in a Y-connected configuration? The current I sub little a capital A is, how is it related to the current going through that Y-connected? I'm drawing in the air and you're going, I have no idea what he's drawing. Here's the picture. This I sub little a capital A is the same current, or that's the phase current in the load. It goes directly through that load. When we now see I sub phi, that's the same as the line current in this Y-connected analysis. And that's what we're saying. We're saying we have a Y-connected load. We have 3 times, and V sub phi we just derived to say, oh, that's V line over the square root of 3. I sub phi is just I line angle of theta sub phi. And now we can clean that up and we can say, oh, there's where the square root of 3 comes from if we now have our quantities known in terms of line voltage and line current. And in fact, we don't even need to know how things were interconnected. You could rederive and get the same formula if you had assumed a delta connected load. Then things would just be interchanged between the voltages and the currents, and we would get the same expression. This now is a useful formula, and if you wanted to, you could now break that out into its components. You could say, well, they told me the total real power. I don't know S sub T. Well, you now know the real part of that if they told you the total real power, the total average power. This is now also the square root of 3 V line, I line, and now we can just use Euler, cosine theta phi plus J sine theta phi. And that now says that P total can be written in terms of the line voltage and the line current and the power factor of that element or device, scaled by the square root of 3. And the total reactive power is now available to us as well. Now we're all set. Now we can start working problems. Here's a problem. Oh, just wondering if you were awake. Have all these forms on the desk. Just thought I would introduce a little bit of a distraction. See if anybody's paying attention. And if you're playing along at home, you have no idea what I'm talking about, but I now have a means of keeping this problem description on the screen or in front of you as we're working through it on the tablet. Now you have a way of saying, okay, what was the problem? I can't even remember. He's scrolled down so far, I can't remember even what we were talking about. Well, now you can refer back to what we were trying to refer to. Here's a question, and this is coming from a previous exam that was given a little bit ago, but in 2019, it was spring of 2019's 320 class. You're now asked to find a single-phase equivalent circuit from the following description. You have a generator, and we're assuming it's a negative phase sequence. And if you were looking for partial credit, what would you do with this? You would start reciting your ACBs, right? So now you say, oh, this is ACB. If needed, I now know how to relate those variables. If you give me a reference phasor, I can now find the B and the C phasor from that information. And so it's now stated that it's supplying a total real power to the inductive system. So now we hope that our Q is up or positive, and the total real power is 140.85 watts. Total says, oh, that's all three phases, and they add up to 140.85 watts. They also are saying there's no internal impedance in the generator. And so you might be thinking, well, let me just start sort of sketching this. I have this V sub little a little n as a phasor, and now they've told me there's no internal impedance to that, so I don't need to worry about something going there, some impedance there. That's zero. It's now just a wire. That's assume there's no internal impedance in the generator. Suppose the line current magnitude is given to be 0.7. Now we know we have something happening here, and the real power absorbed in the transmission line is, and this is now in each transmission line, is 4.85 watts. And you might try to keep track of units. That's not 4.58 ohms. That's 4.58 watts. And this question was not as sharp as it needs to be. I actually should have told them a little bit more information. Let's just assume that the transmission line doesn't have any reactive power associated with it. So let's assume that there's no reactive power in the transmission line. Maybe if I was doing this better, I would say, okay, this is the power of the line is now 4.58 watts, and maybe I would say this is now, if there's no reactive power, my transmission line impedance is all real. And then they tell me something about the total real power. So you have to keep track of what's total, what's each, etc. There's A. And now they tell me that the total real power absorbed by the three-phase load is 127. So I have some P sub phi plus J Q sub phi over here. I now need to find those values. R sub L, Z sub load based on P sub phi and Q sub phi, and my voltage at the generator. And I was told that this had a magnitude I sub AA and that's in RMS. There's many different ways of working these problems, but here is maybe one such approach. But now I find it helpful to start sketching things and try to keep, instead of trying to keep everything in my head and going, what have I found? What do I need? Put it there in front of you, and now you say, well, what do I need to figure out? I need to figure out, can I find my complex power at the load? And if I can, then I can extract the impedance because I know my complex power formula is Z I magnitude squared. I also know what my R sub L is based on P sub little l. And I'm told that initially, well, one of the first things that I was told was over here, and that again was a total real power of my generator. It was supplying to the entire system 141 watts. That's real power. I now know that P sub G total is 140.85 watts. I also know that this, and sometimes just writing these down starts helping you think, what do I really need to know? And this was in RMS, so I don't need to worry about these 1/2 factors floating around. And my formulas were all assuming RMS units. The transmission line, that was per phase. I could either subscript that or not. Let me just keep it as P sub L. I was told that that was 4.85 watts in each transmission line. So now that P sub L is now R sub transmission line I sub AA squared. Or I now know what R sub L is. That was the P sub L over the magnitude of my line current squared. This is now 4.58 divided by that 0.73 squared, or I now know the resistance in the transmission line for this hypothetical problem is now 8.6 ohms. We clear on where that came from. Now we have one of the pieces in our puzzle that we're trying to put together. We've now found the impedance, which is now, by this assumption here, only real. So we found that piece. We have 1 point out of 25. I'm generous with partial credit. Final again, when is the final? A day less than 2 weeks from now, right? Okay, so we need to start thinking about the final. Now what do we do? Well, let's start working with the load. We know on the load side, we were given the total power, and it was balanced. We can just divide that by 3 to find the per phase power. I think it was 127.1. We divide that by 3, and now we have 42.37 watts. What else do we know? Oh, I don't need to keep scrolling. You've got it. Sorry. Whole point of doing 2 projectors. What else do we know? What do we also have? We also were told the total reactive power of the inductive load. That now tells us the sign on that Q. This is now, no. So now we know Q, load phi, is equal to Q total over 3, and it's positive because it was inductive. Or this is now 95.32 over 3, which ends up yielding 31.773 VARs. We now know what the complex power of one phase of our load is equal to. It's P sub L sub phi plus JQ sub L sub phi, which number-wise is now this 42 plus J 32. But that's also, based on the formulas that we derived up above, that's the impedance of our load times the magnitude of our phase current, which is the same as our line current. And we were given that I sub AA magnitude. That was the 0.722. The only unknown now is Z sub L, and it's going to come out to be a complex impedance, which is good. If we now divide that out, we now have this Z sub L phi over I sub AA squared, and that ends up being something a little nicer if you use all the decimal places, 80 plus J60. That now allows us to go back up to this picture and say, oh, this now in terms of its, so this, we can have many different things here to keep track of, but in a single phase equivalent, we're really interested in this impedance, which is 80 plus J60. We now have the impedance of our transmission line, which was real. We have our impedance of the load, 80 plus J60, Z. And now the only thing remaining is a magnitude on that generator for the voltage of the generator. And that was one of the reasons we derived that one formula in terms of all of these line quantities. We now know that for total three-phase power, real power, this is now the square root of 3 V line, I line, cosine of theta total. Do we know the cosine of theta total? What makes up this? in this case, it's now, what does the generator see? It sees the transmission line and the load. We need to add those pieces together in order to get the total impedance, and then we find the angle of that impedance and call that theta sub t. The total impedance now is R sub little l. That was convenient. That's actually what I wanted to have happen. Plus, well, did I even do? I'm not sure I parameterized that. Plus the impedance of the load. And this was somewhere 8.649. We add all of those pieces together and we obtain 88.65 plus J 60. And now we can find an angle of that impedance. That will be our theta total. Theta total is now the inverse tangent of the imaginary piece over the real piece. And we don't go up quite as high as we go over, so we're not even quite up to 45 degrees. And in fact, this is 34 degrees. Do we have everything that we need? What do we have? We were given this in the problem statement. Weren't we given that to be 140.85 watts? We were given this. We had to do quite a bit to find that. We're now going to be able to solve for that remaining unknown, which is our line-to-line voltage at the terminals of the generator. And that won't be quite what we need to get V sub little a little n. We'll have to scale that in what way? By that square root of 3 factor. Capital V sub L is now P sub G total over square root of 3 I line cosine theta t. And plugging in all of those numbers, you end up with 135 roughly. So the magnitude of our A-phase generator voltage is a square root of 3 smaller than that. Or that's now 77.9 volts. Which now allows us to sketch our single phase equivalent circuit, which was the requested information. And maybe I should just do it more schematically. This was now just a resistor of 8.65. This now is 77.9, and we can call that our reference phasor if we want. And over here at the load, it was inductive. It had a real piece of 80 and it had an imaginary piece of 60. And that's now our single phase equivalent answer to this question. Anybody still awake? Questions on that? Yes. Could you have left it as boxes or do the resistors? Whichever you like to draw. Either one would be equivalent. At that point, you've got the answer. Just provide it in a clear way. You could have said, oh, here's a box and it's 80 plus J60, but you should say ohms. Otherwise, somebody's going to say, well, I don't know if they knew that that was ohms or if it was volt amperes or if they knew what they had. So make sure and label it to make it clear to the evaluator what it is that you now have provided. Yes? So now what we are doing in our single phase equivalent, our single phase equivalent is always this YY configuration. Now what we know though is we know that we have this formula that is in terms of line quantities, line voltage and line current. We then have to, in our YY configuration, we just extract the A single phase or the A phase to get our single phase equivalent. We know then that we can't give them little a, little b voltage, which is what V line is. I'm not sure I can. So we know that we have to give them in that formula that is the square root of 3 that we derived, V line, I line, let's say cosine theta phi. This is actually the voltage between A and B. And our single phase equivalent, in fact, is just really working on one of the phases. And so we need little a, little n, and not little a, little b for the voltage. We have to know that. That was the part of the reason I was trying to show these different interconnection structures. And typically we like to play with this. Once maybe somebody gives you a Y delta, you go, ah, really? Well, you convert the impedances of the loads to Ys, and now you have it into a YY, and now you can analyze it as a YY, and you could extract the single phase equivalent. The reason you can extract that single phase equivalent is because in a balanced scenario, you could either put a short from little n to capital N as a wire, or you could just say, and that's what we're doing when we get the single phase equivalent, is you could now sum up V sub capital A capital N plus V sub capital B capital N plus V sub capital C capital N. Those are balanced, and if you add up the phasors, you get back to where you started. That gives you 0 voltage drop or 0 current flowing in the neutral conductor of a balanced three-phase system. The question was, how did I know to get V sub A in from this formula? This formula is in terms of what you might be able to go out into the real world and measure. The line voltage, which is transmission line to transmission line, and current in the transmission lines. And it's not what is in a particular phase. It depends on the interconnection. Other questions on that? Next question. Suppose we have a three-phase load and it absorbs a total apparent power. Did we define apparent power? Everybody's reading their tablets or taking pictures. Hopefully I'm not in front of the picture. Don't want to do it. Is it called a photobomb? That would not be good. What's apparent power? Did we talk about that? Pardon? That's the magnitude of the complex power. Correct. So if you know, or this now tells you something about the complex power, it's the magnitude. And then we may have to figure out, do we know the sign? I'm sorry, the angle. And maybe the sign on that angle. Suppose a three-phase load absorbs a total apparent power of 100 kVA. So if you were just sort of reading this, you might just say, oh, this is now that, the magnitude of S sub T, complex, at a lagging power factor of 0.707. What kind of a load now do you, so we now have total complex power information. That's now 100 kVA. And we're told that the power factor of the load is now 0.707 and it's lagging or what does that tell us if we said what's the angle associated with that power factor? The power factor, remember, is the cosine of theta. We can now do the inverse cosine of that power factor, and now we have to keep track of the sine. What angle gives us a cosine of 0.707? 45. So now we know what theta is, and we know that it's plus because of the lagging. What do we ask for? Let the magnitude of the line current feeding the load equal 25 amps. So we're given line current information. Suppose the complex power consumed by each transmission line. Oh, brother. Now we have to keep track of each and total. Is it clear? The each is just each individual line. We're now told what its transmission line, and this is now given to us in power terms, not in impedance. Find the magnitude in RMS units of the line voltage. Now we're asked for the line voltage, not the phase voltage. This is not a single phase equivalent. This is what's the line voltage magnitude. This is now magnitude of V sub little a little b. So you have to read this very carefully as you're parsing out the information provided in the problem description so that we understand what we need to deliver. Where do we want to go? So we now know the magnitude of the line current. And there again is probably a lot of different ways to solve this. Suppose we just said, well, let me do it this way. I can now produce the complex power in one phase of the load because I know that. Or I didn't calculate it yet. I did in my solution. I'm assuming you did in yours. How do I know what this is? How do I know what S sub LT is? Do I have enough information to find it? I now know the magnitude and angle. I have a phasor form of the complex power. I can now just put it into rectangular form and get the real part and the reactive part. And then, if I need impedances, I can divide by currents, for example. But here, let's now say this is now going to be 100 K times cosine of 45 degrees, which we know, plus J sine 45 degrees, or this is now 70.7 plus J 70.7 kVA. That's the total complex power of the load, extracted from the apparent power and the power factor, where the power factor gave us the angle. Now we can divide that by 3 to obtain the per phase, which now gives us 23.57 plus J 23.57 kVA. We were told that we had a line current magnitude of 25 amps. And we also were told what the transmission complex power was. We were given that directly for each phase, and that was 8 plus J 4 kVA. So if we wanted the total complex power that the generator sees, we need to add up the complex power in the transmission line and in the load, and we have it for one of the phases. Or we now can say, oh, the combined complex power in one phase is now the result of adding the transmission line complex power with the load's complex power in that one phase. And doing that ends up being 31.5 plus J 27.57. We can now obtain an angle that the generator sees due to the transmission line impedance and the load impedance from this complex power P and Q. This is now the inverse tangent of 27.57 over 31.57. Again, we're not going up quite as much as we're going over, so this is a little less than 45. And we know that the total power is this square root of 3 V line I line cosine of theta phi. Most of that calculation was to determine this angle of the transmission line and load combined, to find that theta sub phi. We were given I sub L. We were given, well, no, we know what P sub T is. We could back that out from our apparent power and the power factor. And now the only remaining unknown is this quantity, and we need to just find that and leave it alone because it wanted the transmission or the line voltage at the generator terminals. This now allows us to solve for V sub L, this is now 3 times 31.57. That's 3 times the total power in each phase, and that was K, over square root of 3. The transmission line current was 25, cosine of 41.13 degrees. And this ends up being 2.903 kilovolts RMS. Question. Where did the 3 come from? This is actually the 3 in this is I needed my power or the real power of everything, and I found it right there. I found it for, whoops, I've already turned the page. I found it for the load, and I was given what it was for the transmission line. I needed to add those up, and I found those per phase. Then I had to basically scale it back up to get P total. That's where the 3 came from in, this is now what I'm calling P sub T. Hopefully I'm somewhat consistent. This is now 3 times P sub phi. And actually it includes the K. K was 1,000. Other questions on this? Well, we scored 20 out of 100. We got through 2 problems. Question? Yes, so now this formula for total complex power is in terms of line voltage and line current, and that's what we were asked for in our, am I on the right problem? We were asked to find the magnitude in RMS units of the line voltage at the generator terminals. We needed to then find what does the generator see. It sees the transmission line and the load. We found the complex power of each of those, added them together to get P sub T. Then we knew the transmission line current magnitude, that was 25, and all of that taken together, we actually had to find the reactive piece so that we could find that angle of 41.13 degrees. But once we found all of that mess, then we could find directly what the magnitude of our line voltage was, and that is magnitude of V sub little a little b. It's not the A to neutral voltage. This is the line voltage. Other questions? Yes? In this particular problem, did it tell us what was y or delta, I think is the question, or do we need to worry about y and delta? A lot of times you don't need to worry about whether it's y connected or delta connected. And a lot of times, and that's why this formula is nice, now it's in terms of line voltage and line current, and you don't have to know what's inside the black box. Is it Y connected? Is it delta connected? Sometimes you actually might need to assume something, but you could assume Y or delta and you'll end up with that exact same formula. So that formula is very powerful in that, in fact, somebody didn't have to give you the way things were interconnected. You could still tell them the value of the line voltage at the terminals of the generator. By everyone packing up, I'm guessing we're out of time. And I will see you Tuesday. Homework is due Saturday, correct?